Okay, here's the third lesson, or third lesson recording. Just wanted to take a look at what's on the formula sheet and then give you a worked example on thin air wedge fringes. So there's a number of formulae on the formula sheet, and to be honest, they all look pretty similar, and you've got to work out in your head what's going on. We've done this one much earlier. OPD is N times the geometrical path difference. Very familiar with this now. Optical path difference, whatever it works out to be, is m lambda or m plus a half lambda. And you'll know that that's for constructive interference, that's for destructive interference, and you have to put that equal to whatever you've worked out to be your optical path difference for the various scenarios that we've looked at. Here's the formula for the thin wedge, thin air wedge, which we've done. So that's the distance between two adjacent fringes, wavelength of light multiplied by the total distance between one end of the microscope slide and the other, divided by 2 times the thickness of the object that's propping up the two glass slides. This is the formula for the lens coating. And here's another formula that we haven't even done yet, but you'll see that it looks pretty similar to that one. It's got a lambda in it, it's got a D in it, but this has got a large D. Now, we haven't done this one yet. This one comes on later, which is in interference by division of wavefront. All of this stuff is interference by division of amplitude, and it's a huge section, this last bit, division of wavefront, which is basically Young's slits. Stuff you did at higher, reworked for advanced higher, is quite a short section. So it doesn't tell you which formula is to be used where. It gives you the formula but doesn't tell you what it is. So all that maths I did last lesson, you don't necessarily need to remember all of that now that I've said it. But you need to know where the formula comes from. It would be wrong of me just to plonk down the formula in front of you and say, there's a formula. But you need to know where it's come from. There used to be in advanced higher, you used to have to do the derivation to get to that. You'll not now get a question in advanced higher where you're asked to do a derivation and end up with that, but you do need to be able to use that, and you should have an understanding of where it comes from. So you're all groaning now saying, oh, I've been through all of that. Did I really need to do that? Well, the answer is yes and no. Depends if you're happy with just having a formula plonked in front of you and say, well, there it is, use it. Or do you have an understanding of where it actually comes from? So that's off the formula sheet. Haven't done that one yet. We have done these. I'm going to do a worked example now on the thin air wedge. You got a worked example of the lens coating in the last lesson. I needed a break again. Okay, so optical fibers. Optical fibers are, well, optical fibers. They're used in telecommunications, and we have huge lengths of optical fibers that run right across the black aisle, that come from the various telephone exchanges and right along the main road from Tor through Munlucky, through Och, right through Fortrose. I don't know how much further it goes, but certainly through to Fortrose. There's bundles of optical fibers below the road, and they're forever taking up the manhole covers and putting in new optical fibers. They're very, very thin bits of optically clear glass. Now they make these, and what they do is they use molten glass, and it's a bit like spiders making a spider web. The glass is extruded or extracted through a very, very small hole, and it's pulled out, and as it's pulled out through a very small hole, you've got molten glass, you've got a small hole, thing called a die, and you've got molten glass here, and you put some pressure on the container of molten glass, and you squeeze out the optical fiber, and then you wrap it round and round some sort of drum. It's very, very thin. It's comparable to the thickness of a human hair, which is pretty thin anyway. But you may not find, as the glass comes out, if you don't have the same pressure or the same pulling speed, wrapping it around the drum, the optical fiber can get slightly thicker or slightly thinner. And you've got to be able to manufacture the optical fiber within a certain, what's called tolerance, for it to be any use. And you can check how good your optical fiber extrusion process is by using thin wedges. So how do we do that? Well, we've got a very thin glass plate here, and we've got an optical fiber that the manufacturer has made, and we'll stick it there. And we've got another optical fiber, or the same optical fiber, but it's a little bit thicker, and it's propped up along there with another glass slide, and you've got the two like that. Okay, now we can measure this one's been measured. You always have calibration glass fibers, which are the really, really good ones, and we've got to work out how thick this one is. So there will be samples of these in the factory. And how much thicker, I wonder, is this optical fiber? So we've got fiber A, we've got fiber B, and we know, because it's a calibrated sample which is used as a reference sample, we know that the diameter of this optical fiber is 0.20 millimeters. This optical fiber is obviously thicker, and what we've got to do is calculate how thicker, much thicker this one is than this one. So we need to know this distance here, which is 0.120 meters. We need some light, and we're going to illuminate the whole wedge system with some light of wavelength 590 nanometers. It's monochromatic light, and you're going to put your traveling microscope up here. You're going to have a look through the traveling microscope, and you'll notice that you see some fringes, and the fringes are found to have a separation of 4.4 millimeters. Okay, now what in fact you do is you don't just measure two fringes. What you would in practice do is you'd measure perhaps 10 fringes and then divide by 10 to get the separation between any two adjacent fringes. And what we're going to do is calculate the difference between the thickness of that one and the thickness of that one. Okay, so how do we do that? Well, we're going to use the formula which we came up with last time, which was delta X. This is off the formula sheet, is lambda L over 2D. Then I rewrote that to give D is equal to lambda L over 2 delta X. Now, what is each of these? Well, we've got the thickness. Obviously, this is propped up. This is obviously propped up at this end here, and this is in effect the wedge here that we're going to be looking at. So we've got the difference in thickness will be this distance here. The wavelength of light, the length between one end and the other, and 2 delta X. There's delta X as well. So all we've got to do is make sure that we do all of this in meters, because we've got different units. We've got meters there, which is okay. That's in millimeters, that's in nanometers. We've got our rewritten formula. This is the formula off the formula sheet that I showed you just earlier. So we can do D is equal to lambda 590 times 10 to the negative 9, that's nanometers, multiplied by the length L, 0.120 divided by 2 delta x. And that's 4.4 millimeters, 4.4 times 10 to the negative 3. And if you work that out, that would be 8.0 times 10 to the negative 6 meters. So there's not a lot of difference, but what we now need to do is, this is an extra bit in this question, is find out whether that's an acceptable difference between the two, and that's the reference sample. And the manufacturers have been given what's called a tolerance of plus or minus 5%. So as long as this is within 5% of the thickness of that fiber, you can be 5% out on this, it can be 5% thinner or 5% thicker, then it's acceptable. And this is part of the quality control process, that you have your reference sample, you'll take samples of your optical fiber as it comes out the process, and you'll check it to see what this is. And if this is within 5%, plus or minus 5% of that, then that's a good thing. So is that within plus or minus 5% of that? So what we'll do is we'll work out what 5% of that is. And 5% of 0.2 millimeters is, you can do that, 5 over 100 multiplied by that, and that comes out to be 1 times 10 to the negative 5 meters. So we know what 5% of that is, and what we need to do is, every time you take a sample and you look at this, is this within plus or minus 5%? Is it less than 5% of that thickness? And you can see that 8 times 10 to the negative 6 is much smaller than that by a power of 10. So then it's within 5%, so that's okay. So this fiber, although it is thicker, is within the manufacturing tolerance that's required. So that's a typical sort of exam question, is that you get some stuff that we've just been doing and then an extra little bit added on to the end. Right, okay, so that's 3 separate sessions, if you like. Now, when you put all these 3 together, I'm well aware that this is longer than an hour, possibly longer than an hour and a half. I haven't timed actually what each one is all put together. You'll need to watch each one. You'll need to make notes. I'm going to give you some problems to do. I'm aware that this will probably take more than an hour and a half, but it's become obvious over the last couple of weeks that by me only doing an hour ish of a lecture plus some notes, is that we're falling a little bit behind on getting this course finished. So I'm having to up the amount of stuff I give you, both in chit chat and also in questions, and that's going to actually take more than an hour and a half now. I'll make no apologies for that, because we have got to get finished. We're actually not far off the end of quantum waves, but Mr. Garrett's got a huge chunk of work yet to do, and I need to finish early so that he can take over and get his part of the course finished. In practice, what that means is I don't disappear completely and he gets 3 hours a week. It means that he still gets an hour and a half, and I take over teaching some of his section as well. So that will be more on that later. So that's your 3 lessons with some worked examples. I'm going to say which questions you need to be doing from the Campbell-Robertson stuff, which you will submit. I'm going to say this, I don't need to see this work written up. I have asked you to submit photos, but really all I want to do is make sure you do this, and then the thing I do want you to submit is evidence that you're working through Campbell-Robertson's examples, and I will be throwing in every now and again some exam questions, and this is part of an old SQA paper or a worked example. There you go. So that's it. I'm going to stop, and that's the end of this week's work. This is all for this week, including doing some Campbell Robertson stuff and some exam questions, which I'll throw up as well in a post. So I'll stop for now.